Okay, so I missed in the afternoon there, Judith, your questions that you had about physics. Sorry about that, but I will go through them here. I'll do something similar. So we'll just go through that here. Let me just shrink this out of our way here. Okay, so the first one that you were wondering about was 2B. Okay, so a spring stores 1700 joules of energy and is compressed 0.15. Find its spring constant value. Okay, so the equation for that one, let's just bring up the board here. That is a potential elastic energy equation, or EEP. So you're going to use this equation here. The elastic energy, we'll call it, it's giving me the, here I'm just gonna have to redo this one. Okay, try again. Okay, so we're going to use the elastic energy equation. So elastic energy that's elastic, or E, elastic potential. That's what I call it usually. Okay, so we know that that equation is kx squared over 2. This is our compression or stretch in meters, and this is our constant in newtons per meter. Okay, so let's assume that the question, let's say I had a similar question. Let's say I had, instead of 1700 joules, I had 3800 joules with a compression of let's say 0.26 meters instead of what you had there. So all you would do is you would just take, this is where your joules go, 3800 joules. In the EEP, your K stays blank. Your X becomes this 0.26 squared over 2. Okay, so then you have to solve for the K here. So what we're going to do then is square the 0.26 and then divide it by 2. So 0.26 squared. That gives us 0.0676, and then we're going to divide it by 2. Then we get 0.338 K. K times 0.0338. So then divide that out on both sides. So 3,800 divided by 0.0338 gives us a large spring constant of 100. Let's do, what do we got? Two significant figures. So 110,000 newtons per meter is what it works out to be in the constant. So that was how you would do 2B. Okay, it's just using that elastic energy equation. Okay, so the other one, let's take a look here. Shrink this down here, and let me go to my chat here again and see what you had. Oops, wrong one. Damn it. Close. Close. Sorry about that. Wrong chat. Yeah, we're moving from Google Hangouts to chat because they're going to stop supporting Hangouts in June. Okay, so that's this one we want. Okay. Okay, so then it's over on the other side here. Okay, so you also asked me, let's see here. What? 2B, 3, and 6. Okay, sorry I missed that in the afternoon there. I kind of left at 2 yesterday. I should have maybe made a announcement of that. Okay, so let's do a number 3 or a similar one to number 3 here from our potential equations here. Okay, so if we go to our equation sheet for the number 3, let's take a look what it says here. Okay, again, a spring constant one, so this is going to be a conservation of spring energy versus gravity. So there's going to be no friction involved. So we'll set that one up. I'll set up a similar one without the same numbers. I'll just use different numbers and then work it out. And then you can follow that same process for working this one out. And then 6, we'll look at that while we're at it here. Okay, that's a power one, so we'll do that as well. We'll do an example of that. So let me make up one here for 3. Slide over. Okay, so I'll word it very similarly, but we'll just put some different numbers in there so that it looks a little different. Okay, so let's say I had, well, that's way too big. Let's say that I had a spring constant, a spring with a constant of, let's say, 108 newtons per meter. It's compressed let's say 0.35 meters by a 1.3 kilogram mass. Period. If the spring is released, okay, and the mass is shot up against gravity. Find the height it rises. Okay, so that is a similar one. It's not exactly the same one. So the principle here is we're going to have an elastic energy turning into a gravitational potential energy. So if I draw the situation out here on the side for you, we're going to have this spring here. It's going to shoot this mass upwards into the air, and it's going to go up some height above the where, when it was compressed. Okay, so basically we're going to be looking at conservation of energy. So we're going to convert all the elastic energy or elastic potential is going to get converted into gravitational potential. Okay, and that is the equation that we're going to use. So now what we're going to do is we're going to solve for the height in there. So we have to use the equations for elastic potential and gravitational potential energy. Elastic potential, we looked at that in the first problem. That is 1/2 kx squared, or we'll say kx squared over 2. And gravitational potential energy is mass times gravitational constant of the Earth times the height. And this is what we're going to solve for now. Okay, so everything else you should be able to fill in with the variables up at the top here. Okay, now this is 3 significant figures. This is 2, and G is 9.8 newtons per, or meters per second squared, or newtons per kilogram. And then the height's going to come up in meters. So let's put our 108 in for the Newton meters. Okay, and it's compressed 35 meters, or sorry, 0.35 meters. So that's our x, 0.35 meters squared. And then we have to divide that by 2. And this is going to equal our mass, which was 1.3 kilograms, times the gravitational constant of the Earth, 9.8 newtons per kilogram, or meters per second squared. Doesn't matter which one you use. They both will cancel out. And then we have the h left by itself. So we're going to crunch this number down, and we're going to crunch this one down, and then we're going to divide it out. Okay. Put it down here, I guess. Okay, so 0.35 squared first. Okay, that's 0.1225 times 108 divided by 2. So I get 6.615. I'm not going to round anything off yet. Okay, if you want to do newtons, it'd be Newton. And this would be, one of the meters squared would be Newton meters, which is the same thing as a joule. And this is going to equal 9.8 times 1.3. Okay, and that's 12.74 H's. Okay, now we simply divide on both sides. 6.615 divided by 12.74. Okay, and we get 0.5192. And since we're doing 2 significant figures, we'll round to 2, so 0.52 meters. Or if you like, about 52 centimeters. Okay, so that was number 3, a similar one to that. Okay, so then the other thing that I asked, or you asked, pardon me, was about number 6. So again, let's take a look at number 6. We'll do a similar type one. Okay, so number 6 says an electric motor lifts a crate 65 kilograms, 3.5 meters in 6.4 seconds. What is the power output of the motor, assuming that it is 100% efficient? So power is just energy over time. So what we're going to do is we're going to calculate the energy that it's working against, which is gravity in this case, because it's lifting it off the ground. And then we're going to divide it by the time. So that's what we're going to do. So we're going to do a similar one, though, not that exact one. So, we'll do a similar one, like number 6. So again, if we just say an electric motor lifts a 42 kilogram crate, a height of, let's say, 2.3 meters in 4.7 seconds. Find the power of the crate, or power of the motor, sorry. Assuming it's 100% efficient. So we'll do a similar one. I'm just going to check this quick, Judith, so see what that chat was about. Oh, no chat. Good. Okay, so no problem there. Okay, so what power is you're using a couple equations here. Okay, so power is equal to energy over change in time, or just time if you like, it doesn't matter. So this energy that we're talking about, since we're lifting a crate, is going to be gravitational potential energy. So the power is going to equal gravitational potential energy over the time. Okay, change in time is going to be 4.7 because we're starting at 0. So let's put the equation in for gravitational potential energy, mgh, and the time. And that's what you do. You plug the numbers. So the mass of the crate was 42 kilograms. The Earth gravitational field, 9.8 newtons per kilogram. The height that was lifted off the ground was 2.3 meters. And you did this all in 4.7 seconds. Okay, two significant figures. We crunch those numbers together, and we'll get a power in watts. Okay, so let's do that. 42 times 9.8 times 2.3. So I get 946.68 divided by 4.7. And this is joules over seconds, which will be watts. Okay, divide by 4.7, and we get 201.4, so we can say about 200 watts. Okay, there's two significant figures, so that one is significant. 200 watts. 201 you could even put if you wanted, but if you're going to significant figures, 200 watts. Okay, I apologize that I missed that last afternoon. I left about 2. It was nice outside. I went and did some yard work. So that's what I was doing there. So I'm going to send you this video there, Judith. And hopefully that helps you. Let me know if it does or doesn't, okay? I'm going to get this off to you. As soon as I can find where the off button is to stop. There it is. All right. It's kind of a long video. Sorry about that.